thank you very much for coming along. Wonderful to see lots of people here, from the eldest and most senior sitting right up the front to a whole bunch of first year students as well. So that's fantastic. Don't point at older people. So I'm going to give a very broad overview of gravitational wave astronomy, where we've been over the last few years and where we're going over hopefully the next 5 to 10 to 15 years. For those in the audience who are experts, I apologise, there's not going to be all that much really cutting edge new stuff. I'm going to get you up to about 3 years ago, give or take. And the reason for doing that is the observations and the observatories had been offline, but they've been back online now for a few months. But all of our results are embargoed, so I won't be talking about any of them other than maybe giving a few hints along the way. So let's start our story. It's going to be a timeline. It's going to be that timeline that, as I said, starts a few years ago. If I can click through slides. There we go. When I say a few years ago, it's going to start 1 billion years ago. So around about 1 billion years ago, this happened. This is an artist's rendition, but it's actually an artist's rendition from a numerical relativity simulation. And so what you're looking at here is two black holes. You can tell that they're black holes because they're black. There's nothing to see. But you can see that the image has been put on top of an image of a beautiful stellar background. You can see these two black holes are spinning around each other. They're getting closer and closer to one another because of the emission of gravitational waves taking energy away from the system. As that energy goes away from the system, we'll play it again. As that energy moves away from the system, the two black holes get closer to each other. You can see, if you look really closely and you can squint, you can see little sort of the background space is being distorted. That background space is being distorted because the light, as it passes through past these black holes, is getting shifted and moved all around the place because of the curvature of space-time. And if you look towards the merger, you can see now you're starting to really see some wave-like behaviour that's emanating out. So as I said, this happened around about 1 billion years ago. I'll show you what our uncertainty on that is very shortly. It's large. But around about 1 billion years ago, that happened. Then, a question already, Chaba.
Is that real speed? I mean,
No, that was slowed down so that you could see it. So that was 1 billion years ago. Let's fast forward to the period through the 1980s through to the current day. We built these huge instruments. When I say we, certainly wasn't me, didn't contribute at all. But we have these two humongous instruments, one out in Hanford, in Washington, which is up the northwest of the United States. It's on a nuclear reserve. The other one's down in Livingston in Louisiana, down the south. It's around about 1,000 kilometres away, give or take, a long, long way away. That one's in swamp marshland. There's gators all through it. But what these are huge facilities that have 4 kilometre long arms. It's an interferometer. Lasers get shot up and down these arms to measure minute differences in the distance of those arms, and in fact, a differential distance between the two perpendicular arms. So I'm not going to go into too much detail about how the experiment works. Happy to answer questions about it and talk about it at length over coffee afterwards. But that gravitational wave, or that binary black hole system that we saw before, the gravitational waves from those, the ripples in the fabric of space-time, or ripples of gravity, emanated out 1 billion years ago. They travelled at the speed of light for around about 1 billion years until they hit these two detectors on the 14th of September 2015. And this is the beautiful measurement that we made. The top left plot shows the data. So this is gravitational wave strain on the vertical axis. This is the amount that the two arms changed in distance by. And this is time on the horizontal axis. So to Chaba's question earlier, you can see that the time for the signal lasted only on the order of 100 milliseconds. And you can see in Hanford, we have basically noise on the left-hand side, and then eventually something comes up out of that noise and you get this beautiful coherent signal. In and of itself, that wouldn't have been so fascinating, but of course the observatory that was 1,000 kilometres away in Louisiana collected data at the same time. That's shown in blue here, and that matches up almost beautifully. At the very start, it's just noise, so you have incoherent signal between the two observatories, but then when the signal starts to come up out of the noise, you see that the various cycles in the gravitational wave signal match up, and you get this beautiful beautiful signal that's coherent across 1,000 kilometers suggests to you that it's astronomical in nature. The signal immediately cuts off, which is when we believe these two black holes merge and then start ringing down. Again, in and of itself, actually this part would be truly remarkable, but what's even better is that various astrophysicists were going around countries prior to this event saying, hey, gravitational waves, when we first detect them, they should look something like this. Okay, they should have this very characteristic shape. We know that from solving Einstein's field equations in a computer, what so-called numerical relativity simulations. And when you go away and you do that again for parameters of the system that match up with these ones, what you end up finding is these signals down here, which look remarkably like the actual data that we collected. And even more so, you can do statistically rigorous tests with this, subtract off these numerical relativity waveforms from the actual true data, and you just get noise as you would expect if it's a real signal. So absolutely beautiful. Nobel Prize winning science, and in fact a Nobel Prize was won for this in 2017 for 3 people, but on behalf of the LIGO scientific collaboration. So let's look into this data in a little bit more detail. This is it here. So this is again the Livingston data in blue, the Hanford data in red. The Hanford data has been shifted of order 10 milliseconds, which is the light travel time between the 2 observatories. It's been rotated a little bit as well because the 2 detectors aren't quite lined up, so you get a slightly different signal in both of them, but that's all fully understood. You can take a signal like this and it just looks like a bunch of wiggles on a page. But those wiggles actually tell you interesting physics and astrophysics. Okay, and that's really a lot of what I'm going to talk about today. What is some of that interesting physics and astrophysics that we can talk about? So from a signal like this, we can make plots like this. This is a 2-dimensional marginalized posterior distribution. In other words, it's what we know about 2 of the parameters that go into making this system. And in this case, it's the 2 masses. So we know that there was 2 black holes that merged. One of the black holes had a mass somewhere between 30 and 40 solar masses. Okay, and this is the probability density or the probability distribution for the data or for those parameters values given the data. The lighter black hole had a mass of something like 29 solar masses plus or minus 4 solar masses. So we end up with these probability distributions for the 2 masses of the black holes. We know approximately how far away the system was, but unfortunately, when I said before that they were around about 1 billion light years away, what I should have said is it's around about 1.5 billion light years plus or minus 500 million light years. Yeah, and for astronomers, that's all right. It's near enough, to within a factor of 2 is kind of good. And the reason that the uncertainty on this distance is so large is that there's this degeneracy there with the orientation of the system. So the orientation basically means if the system is face on to you, then it's going to appear louder. So in other words, if it's orbiting like this, the orbital angular momentum's coming out towards you, the system will appear louder, therefore you'll think it's further away. On the other hand, if it's edge on to you, so the orbital angular momentum's pointing away from you, you'll think the signal's weaker, therefore you'll think it's closer. So this is a degeneracy that's hard to get past, but we can in various regimes. So that's sort of a couple more parameters. Overall, this system is described by around about 15 parameters, depending on how you count. Another 2 are the sky position. And this is a map of the sky in some coordinates. And again, you have a probability distribution from where it came from. And in terms of this signal, it came from somewhere there. It's just this massive region of sky where we really have no idea. Okay? The way we understand this is really from getting that time of arrival of the signal in the 2 detectors and then triangulating where it came from on the sky. So the fact that we only have 2 detectors for this first measurement means that we can't do a great job of this. We now have a 3rd detector, which means that we actually have pinpointed the location of some signals to a much greater degree. Okay, so I'll talk about all of that a little bit as we go on, but I just want to spend a couple of slides actually saying how we go from these wiggles to maps like this, which tell us the astrophysics. Because what we want to do is we don't want to just measure wiggles and say, hey, look, I've got wiggles, look at me doing science. What I want to do is I want to say, hey, I've got wiggles, now what's the astrophysics? How did a system like this form? Does it agree with the prediction of general relativity? When we see neutron stars, can we learn about nuclear equation of state? What kind of physics can we learn? So it's important to understand this, and so this is my Goldilocks one-slide introduction to gravitational wave Bayesian parameter estimation, but it's done completely wrong. But hopefully it gives you a good introduction to what Bayesian parameter estimation is. If you don't like the word Bayesian, it's just the type of statistics that we use because we all bow down to Lord Bayes, Reverend Bayes. Okay, so this is Goldilocks. Goldilocks is trying to measure a gravitational wave signal. This is her signal shown in the background. And what Goldilocks is going to do is she's going to come along and she's going to try a gravitational wave signal. So she's going to say, simulate a system with various masses, okay? And all I'm going to do is show you what the effect of mass does, the binary black hole masses here. But she's going to simulate a system with various masses, and she's going to try and match that system up to the data here. And she does this, and she tries it, and she goes, oh, look at this, you know, this waveform is all wrong. The frequency is too high, just like the porridge is too hot. Oh dear, the masses are too low. Okay, so what this means is you can see that the frequency of any subsequent peaks, they're coming in too often, right? Which means that that gravitational wave frequency is too high. Okay, and what that means that the masses of the system are too low. And the reason for that is simply that the higher masses I have, sorry, let me go the other way. The smaller masses I have, the closer a system can get to itself before it merges. And therefore, the faster it's going around and the higher the gravitational wave frequency. Okay? So Goldilocks isn't happy with this. Her porridge is too hot. Her masses are too low. So she goes back to the drawing board. She does another computational simulation that takes 10 million CPU hours. And she comes up with this, and she goes, oh no, my waveform is all wrong, the frequency is too small, the porridge is too cold, the masses are far too high, okay? So she iterates, she does this using a Monte Carlo Markov chain method with her porridge temperature, and she ends up getting just the right waveform, and she therefore knows the right masses, she has the right temperature porridge. Goldilocks is happy. She has the right temperature porridge with some posterior probability. Okay, she knows the masses with some posterior probability. So you do this in a really rigorous Bayesian way, expensive computations. So we do them on the supercomputers, but you can end up with those two-dimensional or actually 15-dimensional parameter spaces that say what are the parameters of this system, and therefore we can start attacking the astrophysics. So the reason I go into this in detail is that I can introduce to you a tool that's been built at Monash and also as part of the OzGrav collaboration. And this is something that we call Bilby. There's a whole story to that. This is the nicest sounding name that we could come up with. Plus it's a really cute marsupial. So you can get some really cute merchandise and things like that. So Bilby stands for Bayesian Inference Library. It is the user-friendly tool that allows parameter estimation on gravitational wave events. It was developed at Monash. These are sort of the first couple of papers that we wrote on this, but this is now the tool that is used every time a new gravitational wave signal comes in to LIGO or to Virgo or anything. This is the tool that gets used to then spit out from those wiggles, what does the gravitational wave parameters look like? What are the values of those astrophysical parameters and how can we do astrophysical inference? It's really easy to use if anyone's interested in getting into this space. It's just a Python code that you can very easily pip install and you're away doing gravitational wave parameter estimation on real data. Okay, but we're not here to talk about software, we're here to talk about physics and astrophysics. So this is a gorgeous plot that's called Masses in the Stellar Graveyard. And what it is it shows every single binary system that we've observed to date with the LIGO Virgo Kagra gravitational wave network. So Kagra is a gravitational wave observatory in Japan, hasn't actually observed anything just yet, but its sensitivity is improving. Virgo is this gravitational wave observatory in Italy that has detected a number of events, and we'll talk about a couple of them shortly, and LIGO are the two observatories that we spoke about at the start. But what you can see here, the horizontal axis is simply just the order in which we've observed them, okay? Nothing more than that. We have around about 90 events. This is up to around about the middle of 2020. The observatories were then shut down. They came back online in May this year, and we've been observing since then, but as I said, they're all sort of embargoed. We don't have results to present about them yet, although I can give you some tantalizing clues as to what's happening. So how do I read this? On the vertical axis is the mass of the system that merged. So if we look at that very far left one, that was the first one that we ever measured. This is called GW 150914 because we're not creative souls. GW stands for gravitational wave. 15, it was in the year 2015, 9th month, 14th day. And what you can see is that this is two black holes that merged. They were on the order of 29 and 36 solar masses, and they merged to create something that was on the order of 60 odd solar masses. Okay? And this is how you read this plot. So if I go back to just showing the whole thing, at the time of this discovery, it was absolutely huge. No one ever realized that 30 solar mass black holes existed in the universe. Okay? There was a couple of people who had made predictions of that sort of thing. Those people who were making predictions of 30 solar mass black hole mergers were also saying that they didn't exist. Everyone was just hedging their bets and no one really knew what was happening. But it was remarkable. We had this merger. It was the first ever measurement of gravitational waves. It was the first direct observations of a black hole or black holes. And not only that, it was in a mass range that no one really thought was going to be the first detection. If you look across now at the 90 detections, this thing's vanilla. This thing's really boring, and we're detecting them almost every couple of days now. Okay, so we never thought we'd say that way back in 2015, but this thing really is pretty unremarkable. Still very interesting, but somewhat unremarkable. I'll talk through a whole bunch of other events, but I just want to mention this second one here. That occurred exactly 2 weeks later, and so people called it the second Monday event because the first one happened on a Monday and then the second one happened on a Monday just 2 weeks later. And there was a bit of nervousness in the collaboration that maybe events only happened on Mondays. And anyway, luckily the third one wasn't on a Monday and everyone was relieved. There was some thoughts that maybe it was some weird trucks driving nearby or something. Jabba.
Have you ever observed two events on a day?
Yes, we have observed two events on a day. I think the first time that happened was the 21st of May 2019. Please, if anyone knows, don't correct me if that's wrong. But yes, we've observed two in a day. What I think you're going to get at is there a possibility that we're seeing lensed systems? That's not what you were going to get at.
No,
okay.
I was just going to ask how you call them, but please.
Oh, okay, all right. You've opened up a whole can of worms here now. So technically, GW 150914 is now known as GW 150914 underscore, and there's 6 more numbers. I don't know what they are and I don't care. What I can say is that the collaboration put together a really big committee to sit down for a long time to think about what that would be. There was a lot of fights, a lot of emails, a lot of disagreement. It's not a happy place when you start talking about naming conventions, so we won't go into that in any more detail because we'll offend at least half of the audience, okay? So if you think university bureaucracy is bad, try a collaboration where no one gets paid. All right. Okay. So this is all exciting. These are vanilla black holes, but what was truly exciting was when we measured this thing down here. This is an event called GW 170817. So it happened on the 17th of August in 2017. And what you can see is the masses of this are significantly lower. So as we were talking about before, if the masses are lower, this means the gravitational wave frequency is a lot higher. So when we say that this thing was in our band for about 100 milliseconds, this thing was in our band for around about 60 seconds. Okay, it spent a long time being observed as a gravitational wave signal. So this is what the gravitational wave signal looks like. You can see it's now a time frequency map. So on the horizontal axis is the time. The time of merger is at 0, okay? And we've truncated this plot just at the last 10 seconds because before that you can't really see it by eye. But this is the trace shown in sort of a greeny yellowish color. This is basically the power in gravitational waves as a function of frequency and time. And you can see this very characteristic chirp shape that it makes. It starts off here at around about 60 hertz, But of course, we're sensitive down to about 30 hertz, which is why it's in our band for so long. And then it very quickly rises through the band in the last sort of death throes of that merger before merging at t equals 0. And we in fact lose it at around about 400 hertz, which is something to keep in mind for much later on in the talk. This in and of itself would be remarkable, except that I've left so much white space on this page indicating something's going to come up, and that is this. So this was the event that we detected, and a whole 1.5 seconds later, 3 different gamma ray observatories on 2 different satellites observed an excess of gamma ray photons, which looked like a classic, what we call short gamma ray burst. And up until this time, we'd believed that these kinds of things came from the merger of 2 neutron stars, but this was the first evidence for that. It's worth so this happened on a timescale of 1.5 seconds, came from the same patch of the sky. Because we had 3 observatories detecting this in gravitational waves, instead of it being a huge area on the sky, this thing was actually pinpointed to around about, I think, 32 square degrees, something along those lines. So we could actually pinpoint it to a reasonably small area. And what that did was enable a lot of telescopes, in fact, almost every telescope on the world that was active at the time, to go and stare in that region of space. And so here is a very boring, very ugly, nothing special galaxy taken by the Hubble Space Telescope, an image taken by the Hubble Space Telescope some 6 months earlier than when that event took place. And of course, here is an image taken by a 1-meter telescope on the day of the event, around about 11 hours after the gravitational wave signal. And what you can see here is a whopping big red arrow, which is always a good indicator that something has happened. But this whopping big red arrow points to the only dot on this image that is in this image but not in the other image. Okay? And this was that first optical signature of this counterpart to this GW gravitational wave event. You can watch this unfold in a little bit more detail, and so now you're seeing this is a spectrum of that event in the sort of optical and UV. It started off very bright. This is now over a period of sort of 11 days. Started incredibly bright, very blue, and then dimmed and became purple and then ultimately red. And what you can see, if I'll play this one again, so this is over a period of some 11 days. Is that playing this time? Yep. You can see the blue dots forming there, and then it becomes a lot redder as it evolves. This is actually the nucleosynthesis of heavy elements taking place. So I'll show you a video in a moment, actually I'll show you a video now. So what you can see here, if this plays, why does some play and others not? This is the 2 neutron stars. They're circling in on one another. They're getting closer and closer because of the emission of gravitational waves. This is an artist's rendition. And then of course, boom, it merges and you launch these jets that drive up out of the orbital angular momentum axis. Lots of material that gets sent up into the high up into the interstellar medium, forms a shock front as it plows into that interstellar medium. That creates the gamma rays or various shock fronts within that jet, create gamma rays right at the start. I'll play it one more time. Shock waves create that initial gamma rays, and then in the tails, you can see all of that, the tidal tails, as matter gets flung off in all directions, you see that, here we go. So the shock comes up, you get all of this material going off in all sorts of directions. That's that optical and UV afterglow. That's where you get the nucleosynthesis of the heavy elements. The gold that's in your wedding band or that's in your phone and things like that get created in collisions like this. So this was our first binary neutron star merger that we observed. Absolutely gorgeous event, and it was observed across the spectrum, across multiple wavelengths. So I want to dig a little bit further into what these binary neutron star mergers are. This is a really nice diagram that Carl Knox from Swinburne, he's the sort of Osgrav artist in residence, created for a review that former PhD student Nikhil Serene and myself wrote, and we wrote it about post-merger remnants. So the idea here is I have 2 neutron stars. they're coming together and they coalesce and they eventually merge. Okay, so panel A is them coalescing, B is them merging. There's some artistic license here that I'll talk about very shortly. But what happens immediately after that is a couple of different possibilities. You can immediately form a black hole with a disk, with a torus of material that's been flung off, and it accretes back onto the black hole, launches this jet up, all this beautiful and exotic science. Or you can actually create what's called a hypermassive or a supermassive neutron star that's left behind. Again, you may or may not be able to launch a jet out of that. That's a contentious point that I'm not going to get into today. But if this does happen to take place, then this thing can survive for a period of time before it eventually collapses to form a black hole, or it can settle down into a neutron star. The timescale for this is on the order of a second or less, and that's where you really quench a lot of the differential rotation in that star. If you quench the differential rotation in the star and it leaves behind a long-lived neutron star, that thing can rigidly rotate for anywhere up to a few thousand seconds before collapsing to a black hole, or it can just create a new neutron star completely. Now, what do we learn from gravitational wave observations about all of this? There's a couple of key aspects that I really want to get into, and I'm just going to sort of treat this reasonably coarse-grained, but there's some, I'm sure, condensed matter physicists in the audience who might be interested in this type of thing. But the equation of the neutron stars are 10 kilometers big, give or take, something that we don't know, but they have a mass of around about 1.5 solar masses. So these are laboratories for condensed matter physics that we just don't understand. We think the interiors of neutron stars at this early phase, when they're old and relatively cold, we think they're in a superfluid state. They're probably superconducting. They have incredibly strong magnetic fields. Something like a neutron star like that would have a magnetic field maybe between 10 to the 8 and 10 to the 12 Gauss. Okay? Up at this phase, it probably has a magnetic field 10 to the 15, 10 to the 16 Gauss. Strongest magnetic fields in the universe, most dense matter. And so we don't understand what they're made of. All right? So, you can do quantum chromodynamics calculations and you'll struggle to get out what we call the equation of state of nuclear matter at these nuclear densities, or super nuclear densities. So the gravitational wave observations allow us to actually probe these equations of state. So during that in-spiral phase, we probe what's called the cold equation of state. So these neutron stars here are probably only around about 10 to the 8 Kelvin, right? So really cold. That was a joke, feel free to laugh. They're really cold, and they're really cold because they're still in this state where the lowest energy state is basically a superfluid. Okay, so the neutron star behaves like a cold Bose-Einstein condensate, just a really big one, and you can measure the deformability of that neutron star to try and understand the equation of state. And in fact, this is what we've done with that first GW 170817, and we have really loose constraints on the equation of state of nuclear matter. But one of the remarkable things that you can do next is you can try and measure what's called the hot equation of state during this phase. And it's actually, if it merges and creates a neutron star, which we believe probably upward of 60% of mergers create a neutron star that lives for at least some period of time, this will emit incredibly strong but incredibly high frequency gravitational waves. So instead of being in the hundreds of hertz, it'll be in the kilohertz regime. But it's this regime where you can actually try and measure conditions in the universe that you can't get anywhere else. So to explain that, we've got a little phase diagram here where you've got sort of density of material on the horizontal axis, temperature on the vertical axis. It's just a schematic, so the axes aren't really labeled. This is about nuclear density. Up here you've got supernuclear density, and this is sort of temperature, where really it's not until you don't lift up off this temperature axis until you're in the very, very early universe. So a normal star, you can be anywhere near the temperature of the sun, and you'll still be on this horizontal axis. You're basically at zero temperature as far as a diagram like this is concerned. The particle accelerators, this is sort of the type of regime they probe. Neutron stars are all the way up here. And they're all the way up here in a region where you may or may not expect some kind of phase transition to some kind of quark gluon plasma. Okay, so you can potentially have deconfined quarks, colour superconductors, all of these things that I don't actually understand, but seem to be very interesting for nuclear physicists. So that's where a cold neutron star lives. It lives on the horizontal axis. As I said, it's only 10 to the 8 Kelvin. These proto-neutron stars, as soon as they're born, they actually live in this hotter region. That they actually get up to something like 10 to the 11 Kelvin. For those of you who don't know what 10 to the 11 Kelvin is, it's on the order of 100 MeV, give or take. Okay, so incredibly hot. So if you look at the shape of this sort of deconfinement region, or this transition, this where you expect these phase transitions to happen, people don't know where they happen, but it's somewhere around here, give or take. There's a chance that these hot neutron stars could actually have some kind of core phase transition that allows you to probe matter in these really exotic states. But we have to be able to observe them, okay? And this is a problem. So with that one gravitational wave event I was talking about before, the binary neutron star merger, we did not probe any of this physics. We simply couldn't. The gravitational wave frequency was too high for our observatories. The electromagnetic observations, they were sort of good enough, but not really to really be able to probe anything here. We didn't get onto them quick enough and various things like that. So one of the things that I'm going to talk about in the last sort of 10 minutes of my talk is actually how do you build an observatory that probes the region up here. Yeah, Elliot.
What's the uncertainty like on the temperature?
The uncertainty on the temperature. If you ask a numerical relativist, they'll say they know it really well. I'm skeptical of that. It's one of the reasons, so people simulate this and there's a lot of physics that goes into it. I don't think they get heat transfer exactly right. The other thing they don't get right is magnetic field evolution, which I think can affect the dynamics. But you expect, these two neutron stars merge, you get a shear interface. At that shear interface, it heats up. And that's where you get that sort of 100 MeV. I'd believe that, but how it cools exactly after that, I would say is uncertain.
It's just Alice measured the deconfinement / the chiral transition temperature. It's about 140 to 170 MeV.
Oh, bugger.
So it's right there. So depending on where your uncertainty is, it can go either way.
Yeah, interesting. Okay.
Depth of evolution was 10 MeV, not 100, right?
I can't do the maths in my head. No, I thought it was closer to. I thought it was a bit under 100, but I didn't think it was as low as 10. But I'm factors of a few off in all of my. I'm just order of magnituding everything here. So don't fact check any of my numbers. Simulations do vary between that shock interface being on the order of 50 MeV, and some of them get up to over 100 MeV. I don't recall seeing one as high as 140. But again, what's a factor of 2 between friends? Presumably that temperature is going to be density dependent though.
Yeah, I think so.
Yeah.
It's just whatever density they manage to reach in the LHC with those collisions.
Yeah, right. So we're at about 4 or 5 or 6 times nuclear density here. Okay. That's fundamental physics. That's really interesting stuff, but it is just for the astrophysicists in the audience. It's worth saying you learn a lot more from these types of events. And so just sort of a little bit of a laundry list. Obviously, the gamma ray burst physics is really interesting. How do you even can't speak now. How do you even launch jets out of these things? Can you launch jets from this phase, for example, or do you need it to collapse into a black hole? And what's that mechanism? You've got magnetic fields that wind up and go through the black hole apparent horizon or ergosphere and things like that to launch the jet. The actual formation of black holes, as I said, there's a lot of heavy element nucleosynthesis going on here, so it really is about the chemical enrichment of the universe, something that I know the STARS group works on a lot here, and Amanda's worked on a lot in terms of, I can't spell element. Anyway, of course there's interstellar medium and extragalactic physics that we want to understand that you can get from these types of events. And actually one of the big things that I'm not going to talk about today is cosmology. And it turns out that events like these are standard sirens, and so they actually allow you to do cosmology, which is complementary to all forms of conventional cosmology that we've been doing for decades. And so things like the Hubble tension, for those that have heard about this, may or may not be solved by trying to understand gravitational wave cosmology. And if you're interested, we have a DP and come and work on it. Good. So that was that event, and at that time we thought we understood everything that was going on. And I just want to very quickly go through another couple of events. We detected a second binary neutron star merger. I've been trying to call this the Anzac Day event, but no one is following on. So if you can, please do that. Happened on Anzac Day in 2019, so the 25th of April. And this was another neutron star merger that we thought was really nice and simple and sort of garden variety, and everyone was very excited. It was the second ever binary neutron star merger. But it turns out we don't understand it at all. And the reason that we don't understand it, people like Ilya and his group, they try and understand what masses binary neutron star systems should have. And you can follow through the whole life cycle of stars, and there's a lot of work that gets done all through the department here about that. And what you end up observing, at least in the galaxy, is how massive binary neutron star systems are, and when you calculate their total masses in the galaxy, this is the masses of each double neutron star system in our galaxy. Okay, and they all fit in a really tight mass distribution. And prior to 2019, in April, we thought we understood that. Everyone was happy. It was all hunky-dory. Turns out that this system was far too massive and is completely unexplained. Okay, and so we don't really understand exactly how a system like this forms. In blue and orange are just the posterior mass distributions, the posterior distributions on the total mass for this event, given different assumptions, which aren't too important here. All this is saying is it's robust to the assumptions that you make that this thing is far too massive compared to all of our galactic systems. Okay, and so that's really the key takeaway, is that if you want to do the work that Ilya and all of his, the Compass group and things like that do, they can't even explain the second binary neutron star merger, so they need to get their act together.
You can't even explain the first one.
You can't even explain the first one, fair enough. So you go from the, is it a phrase? You go from the ridiculous to the sublime. You go from this event, which was really quite not very massive, and then all of a sudden we measured this event, which is called 1905-21. This is on the 21st of May 2019, and this is the one where we measured two events on that one day. One of them was very interesting, the other wasn't. This was, at that time, the most massive neutron star black hole merger that we've ever measured in all three detectors, and you can see their gravitational wave signals here. It was really pretty loud. But what was really interesting about this, not only was it the most massive system to date, but we actually showed, so Isabel Romero-Shaw was a PhD student here with myself and Eric. Eric and I showed that this system actually has an eccentric orbit. And that's weird, okay? So what you actually expect with normal binary black hole systems is that as they spiral in over many, many millions or even tens of millions or hundreds of millions of years, they actually shed any form of eccentricity because they circularize. When they're at closest passage, they emit more gravitational waves, which causes them to actually circularize very quickly. So you don't expect, if systems are formed as a binary stellar system, you don't expect them to have any residual eccentricity by the time they merge. Now, what's really cool about this event is that people like Alex would also tell you that this event shouldn't exist because it's far too massive. And there's systems, and there's a thing called a pair instability supernova, which basically says that when stars are above a certain mass, when they go supernova, instead of collapsing to form a black hole, they actually just blow off all of their material and nothing's left behind. So you actually expect a gap in the mass distribution of black holes above 50 solar masses. Yep, sweet. Above about 50 solar masses. Again, Alex doesn't really know, but this is one of the things maybe we're trying to measure. And so how does a system like this form? Well, the combination of these two things tells you that it's probably something like a dynamical merger or a second generation merger. And so the idea here is actually this system didn't initially form as two stars that then spiraled in and eventually merged, but instead they formed as two stars, actually three stars at least, all off separate to one another. Maybe there's a star system over here, a binary star system that goes supernova, both form black holes, collapses, forms a black hole, and it is that black hole that then finds another black hole in a dense stellar environment like a galactic cluster, something along those lines. Eventually, those two find each other and merge really quickly because they're on this really chaotic orbit, really sort of extreme path which means that they just find each other, do a couple of slingshots past each other, and then merge with some really high residual eccentricity. So it's a pretty consistent story that sort of is starting to hold together, that a system like this is what's called a dynamical merger formed in some kind of dense stellar environment. The big question for us now is how many other systems actually form in dense stellar environments versus how many form in binary star systems. And again, this is something that Eric, what's your name? Ilya's group can't actually tell us, but they should be able to tell us. So in particular, Rio's been working a lot on, common envelope phases through these binary interstellar interactions and things like this. It's a mess. There's some beautiful, gorgeous physics here, but we really need to understand how these systems formed. And from the observations, we're starting to get a bit of a handle on that. Okay, so we didn't know anything about the last two events. We certainly don't know anything about this one. This is an event called 1908-14. I've hidden it behind here because you don't care what the secondary is, or what the primary is. But in fact, the secondary, so the lighter object in this merger, is something that we don't understand. Okay. Now, we don't understand it for a couple of reasons. This is the mass of that lighter object. Again, the two different colours are just two different assumptions. So this is all just to say that whatever mass you measure, it's robust to the assumptions that we put into our modelling. And this thing has a mass of around about 2.6 solar masses plus or minus 0.1. So we measure its mass really accurately. And that's a really big problem. Because if you're a theoretical neutron star physicist, you would tell me that masses of neutron stars can't be above about 2.2 solar masses, give or take. And in fact, that's what these vertical lines are. These vertical lines are really trying to push the envelope on both theoretical and observational models as to how massive neutron stars can get. And simply above a certain mass, a neutron star will just collapse in on itself and it will form a black hole. So, great, that tells you that that's a black hole. Okay, it tells you it's a 2.6 solar mass black hole. The problem is that the primary is something like 24 solar masses. And again, the people who do population synthesis will tell you simply cannot create a system that is 2.6 solar masses plus 26 solar masses. Okay, there's just no way of doing it. Well, there is, because the universe gave us one, but we just don't know how to do it. So we don't know if this is a black hole or a neutron star. Maybe it's a really rapidly rotating neutron star, which is why it's allowed to be more massive. I don't like that for a whole bunch of reasons, but a lot of people have written papers about that. But really, this is a great mystery that we don't understand. You can tell by this point, all I'm doing is pitching for more funding, right? Because we don't understand stuff and we need to, therefore there's interesting physics and astrophysics. Just to sort of drive through, we do understand these systems, and in fact, Rory Smith, who's in the room, who worked a lot on these, there's a typo here, but this is two systems that were observed late in the third observing run, GW 2000 and 2001-05, and I think it's 2001-15. These are the first ever neutron star black hole, bona fide neutron star black hole mergers that we observed. So these are the legitimate neutron stars merging with black holes, and that's interesting for a whole host of reasons. So very quickly, what are we doing here? We've sort of covered off on a whole lot of things. This is a couple of sort of subset group photos that we took in and out of COVID. So there's a degree of seriousness on some people's faces here, and Ilya's doing a dance. No one knows why. And then we went on a little sort of LIGO group retreat, which is the photo in the top left as well. We're working on a whole bunch of different projects, which I sort of want to just give everyone a flavour of. A lot of them, at least in terms of the LIGO group, are working on these astrophysical inference problems. And so the idea is we've built this software that enables us to take the data and work out what the physics and the astrophysics is, and we're exploiting that as many ways as we can. So this is in particular doing things like tests of general relativity. Yuri Levin's here, which is wonderful to see him back, and hopefully he'll stay for much, much longer than what he's proposing. But Yuri, Eric and I wrote a paper way back in 2016 actually saying that we can detect this weird effect called gravitational wave memory, which is actually a permanent distortion of space-time every time a gravitational wave passes through. So we're building on that. We've had two PhD students, so Moritz Hübner, who's now graduated, and Chun Chung, who's working on this search now, really trying to understand how gravitational wave memory works and how we can actually make an observation of it. We're trying to understand whether black holes have hair. And this is a really weird thing. I don't, but do black holes? So the no hair theorem basically says that black holes should be fully characterized by just two parameters, their mass and their spin. But it's actually a really hard thing to measure it for various reasons. And Teagan-Clark is driving that project forward. All of this neutron star equation of state stuff, black hole formation, how do black holes form, and not only that, but if you look at, rather than just individual events, you can study the populations as a whole. And that's something we're really driving forward now. Particularly a lot of Eric's students have been really working on that. Christian Adamsevich and Hui Tong and various others who I'm sure I'm missing have been working on really trying to understand at a population level what kind of statistics can you do, linking in with the population synthesis and sort of trying to bridge that gap between the population synthesis that you'd expect and what you'd observe. Neutron star black holes, bursts, there's all these other types of sources that we expect to hopefully see in the next couple of years as well. And of course I mentioned briefly the population synthesis things, the formation histories, common envelope physics, supernova physics, there's a whole host of things that are being done. So in my last 5 minutes I want to just provide a roadmap of where we're going and where we really want to go. Let me skip past that plot in the interest of time. So this is a timeline. This is a beautiful plot that was made by Fleur Brookgarden, who visited Ilya here for quite a while. She's now tenure at somewhere?
For the time being, she's at Flatiron, but at Columbia.
All right.
But she's going to Johns Hopkins.
All the good people go to Columbia, I hear. So what this shows is the number of events that we've detected as a function of time. And what you can see is that this was our first observing run, and we got a couple, and then we got up to sort of on the order of 10 events. And then all of a sudden we got up to on the order of 100 events. This is binary black holes, this is binary neutron star systems, and in whatever color that is, it's black hole neutron star systems. And from here, you're then projecting forward, given the improved sensitivity of our instruments. And what you can see is that this is a log scale. And these numbers grow really quickly. So at the end of the third observing run, we had detected around about 90 binary black hole systems and a handful of other systems. We expect that number to grow up to on the order of 1,000 within the next few years. And not only that, we expect it to jump up to on the order of 10,000 sort of by the end towards the end of the decade and soon after. And the reason for that is all of you boring electromagnetic telescope people, your signal to noise ratio drops off of 1 on the distance squared. Ours just drops off like 1 on the distance. Okay, so the better you make your detector, the further out you reach into the universe by a linear factor rather than by an inverse square factor. And that's really, really powerful. What you can see though is up until around about the mid-2030s, this sort of increases just a little bit at a time, and on a log scale it's still really impressive. But after that, we're hoping things jump up absolutely rapidly. But that requires the next generation of gravitational wave observatories. So what we have here is sensitivity curves for gravitational wave observatories. Let's actually skip over that in the interest of time. What I'm showing here, this is the same sensitivity curve, but I'm going to introduce it a little bit more slowly. So this is the gravitational wave frequency. I mentioned that we normally look in the sort of 30 to 100 hertz regime. This is our how sensitive we are. So the lower the curve, the more sensitive you are, okay? And this is the thing that goes linear with distance as well. So you can see where I've got certain sensitivity. This is around about now, give or take. At full design sensitivity, you push down by another round about a factor of 2, give or take. So this is in the next few years. Then you can make another leap forward. This is an old plot. It was supposed to be by around about 2024. It's probably going to be about 2025 now, give or take. You get up to this regime where this is something called A+, stands for Advanced LIGO Plus. This is mostly funded and it's minimal technology risk. There's not too much potential problems here, although there are a couple of issues that people can ask me about. And you get sort of on the order of a factor of 3 improvement, give or take, across the band. After that, we don't really know what will come next. There's a lot of proposals. Some of the proposals are these things called Cosmic Explorer and Einstein Telescope. And they are a full order of magnitude more sensitive in the sense that that means you can detect every single merging black hole throughout the universe. So you're actually sensitive to them out to a redshift of 1,000, or in other words, as soon as they start forming in the universe. Okay? The problem with these is they cost around about $3 billion, give or take. That's in today's currency, so next year it'll be $4 billion. They're not funded, and it's really a lot of uncharted territory in terms of technology. So as an example, these are, rather than being 4-kilometre arms, the Cosmic Explorer in the US proposal is 40-kilometre arms. And of course, even just building a 40-kilometre straight arm is a problem because the Earth curves a lot, right? So on 40-kilometre distance, the Earth curves by about 20 metres. So just your dig and fill is going to cost you an awful lot of money, let alone the technology to shoot a laser, very, very high-powered laser beam, incredibly straight, 40 kilometres, and get it to bounce up and down your tunnel multiple hundreds of times. Okay, so this is difficult. This is difficult. We have an interim proposal, and our interim proposal is something called NEMO, which stands for the Neutron Star Extreme Matter Observatory. The scale is not quite as big. It's on the order of a couple of $100 million. And what you can see from the sensitivity curve is that just at low frequencies, it does a really terrible job. It's horrible, okay, by design, because that's where the cost is. It's really expensive to get low frequencies. Up in the mid-frequency band, it does reasonably well compared to sort of A+, but up in the high frequencies, you're actually getting up to the same sensitivity as that full third generation detector. And the reason that's good is it targets that neutron star science that we missed out on with GW 170817. So if you go back to a figure like this, what we're actually targeting is really this late in-spiral phase and this very early post-merger phase. So a proposal like this has the potential to make the first ever discovery of a post-merger remnant. Okay, it's not guaranteed, and that's sort of shown in the details of this plot, but I'm running short of time, so I'll just sort of skip over that and happy to discuss it. Of course, there's a multitude of science cases for this, not just neutron stars. You could also expect to have supernovae emitting up at those really high frequencies. So if a supernova goes off within a few megaparsecs, we would hope to be able to detect it. You can detect quote-unquote mountains on neutron stars. If a mountain is on the order of, I don't know, less than a millimetre on a neutron star, then as that neutron star rotates, it'll emit gravitational waves. It'll emit them up at these high frequencies, and you can try and detect those. And there's a whole bunch of other, the unknown unknowns, and even some of the known unknowns that are really potential for observations there. So I will leave you with my final two slides. This one just says that we're actually developing a plan to try and build something like this in Australia. It's very, very early days, but we've formed what has a name of the Australian Gravitational-Wave Australian Gravitational-Wave Observatory Project Executive Committee, which is tasked with really developing this plan and setting this forward and progressing it. I'm chairing that committee with a bunch of colleagues from around Australia in Ausgrav, and we're really trying to understand what the funding landscape and everything looks like with that. And I will leave you with one final thought. AI is all the rage, so I asked AI, should we build a gravitational wave observatory in Australia? And this was the response. There's a few phrases in here about government support, which you may or may not agree with, but other than that, AI is excellent for doing these kinds of things. So thank you very much for having me. I can do it. I'm happy to take questions. We'll go with Mark first.
For your NEMO sensitivity plot, what are the points where it's dropping in sensitivity compared to the other ones that are more consistent?
Yeah, great question. So we were just a little bit more honest in our modelling, and that's all it is. They know about these kinds of things, and so we want to understand whether there are issues. Basically, what a lot of these lines are is that you have your mirrors at the end of your vacuum tube, and they're suspended by multiple stage pendular systems. And those pendula have a fundamental resonant frequency. And this is basically those in the overtones. There's a lot more cool stuff. Like when you look at, so what's ignored in sort of the A LIGO ones here, but we see in our actual real sensitivity curves. For example, there's this beautiful 50 hertz line, which is just the power frequency of in the US. You know, there's so many lines like this that appear. Because our signals rush through the band, they don't affect us too much, mostly. But you know, they can be a data analysis challenge, but we expect them and we know what to do. I'm going with younger people.
How do you achieve the sensitivity in the high frequencies?
High frequencies. Yeah, power. So the more power you pump into it, the more sensitivity you get up at high frequencies. And the problem generally is that as you pump power in, and I can't remember the scaling, how it goes. Does anyone? Anyway, as you basically you turn up the laser power, the way I imagine it as a theorist is you just grab the power knob on the laser thing and just... as you turn up the power, it introduces a lot more instabilities and various things in the interferometer as well. But we worry a lot less about them because we ignore these low frequency regimes. So yeah, it really is at this point just about power. Now the problem then is that you heat up everything as well. So you heat up your mirrors. When your mirrors heat up, they deform. You have to act against that. You have to do a whole bunch of things. But very smart people like Yuri and Rory and other smart people around the world work on these kinds of problems, and we're hoping we can mitigate against it.
Does it affect your long-term running costs?
Not in a big way, I don't believe. Some of the big costs are air conditioning anyway, and things like that. But look, one thing, running cost is not something we've fully estimated at the moment. Typical sort of order of magnitude estimate is they're around about 10% the scale of the initial outlay. But there's a lot of uncertainty around that number, and that's one of the things that we need to investigate. Sarah.
What are the lowest mass sort of mergers do you think you'll pick up in NEMO?
Oh, yeah, good question. Look, you pick up the lowest mass things that exist because low mass merges at higher frequencies. So neutron star mergers, we should absolutely get them. Do objects merge at less than a solar mass? I don't think so, but Alex is nodding his head. Amanda's agree. Sorry, I should be much more specific. Do black holes less than a solar mass merge? Sorry, yes, stars and white dwarfs less than a solar mass merge, but they merge well out of our band because they're the surface of the white dwarf touches and things like that. So we don't measure them. To get a black hole less than a solar mass or less than even 2 solar masses, it probably needs to be a primordial black hole. So it needs to form very early universe from primordial fluctuations. I don't buy into that for various reasons, but we look. People within the collaboration certainly look for events like this. I'm going to go with Ulrich and then Alex. Yeah, younger than Alex, and that's all that matters.
Can you explain in an easy way why you get the 1 over distance rather than the 1 over distance squared?
Yeah, it's because it's an amplitude rather than an energy measurement. So we measure the amplitude of the gravitational wave. So the energy absolutely falls off like 1 on distance squared, but we don't measure the energy, we measure the amplitude of the signal, which...
I naively thought that all gravitational waves were quadrupoles, and therefore that you would get a quicker fall off, as you do for an electromagnetic quadrupole.
No. So the quadrupole falls off like 1 on the distance squared. You do get higher order terms that fall off faster, but it is the quadrupole that falls off like 1 on distance squared. If you want a more nuanced answer, turn to the person to your left, and yeah, he'll be able to whiteboard something up for you over an hour. Alex.
Can you go back to the background slide for the mergers? So what you show there is okay.
Yeah, sorry, I just want to get it up.
All of these things merging that has been seen, but I assume there is at the present some selection bias, so this is not the true representation of the actual black holes merging, and so it will need to help you with ironing out the slower part of the distribution.
Okay, so that's good. So if anyone didn't hear, so Alex points out very rightly that what we're seeing here is not the true representation of mergers in the universe, but there's a selection effect. We measure heavier stuff better because they emit stronger gravitational waves. But then you reach a point where stuff that's too massive, you also don't measure because they merge at frequencies outside of our band. So the question is, does NEMO help fill in this gap? I think it does a little bit, but I think by the time you're online with NEMO, you've probably got it filled in at least enough anyway. So I don't think that's a main science driver, but it's an interesting question. Yeah. Yeah. Well, I'm just going to keep going until you tell me to stop, Amanda, which is probably 2 minutes ago.
I mean, maybe just another couple of questions.
All right. Oh, this one scares me. Yeah, we'll go one.
It's not a scary one, I promise. Some of your, I think the previous part you were showing, we showed the future instruments listed circa 2024 for A+. That seems a bit optimistic. We're 4 months away. So I'm wondering what the current prognosis is in terms of timelines.
Yeah, look, so A+ is actually the 5th observing run. So we're in the 4th observing run now. The plan for the 4th observing run is to go for about 18 months with a 2-month gap in between. So it started late May. So May plus 20 months takes you through till mid-ish 2024. I think the plan is for a year to a year and a half shutdown and then online. So it's around circa late 26, I believe.
Oh, so we're not actually doing a design sensitivity. We're just jumping straight over that into...
Look, it's really... to some extent, because some of the technology for A+ has been put in, you know, it shifts around a lot. Things like the quantum squeezing, you know, is in there early and things like that. So exactly how they were defined as strictly being design sensitivity versus strictly being A+ now is shaky ground. Not only that, but the biggest concern is the low frequency noise. That there's low frequency noise that no one understands, and that we can't seem to be pushing that down. So whatever sensitivity we get to at this stage looks like it won't be that kind of design sensitivity anyway.
One last question. This was a quick one.
Is it true that you've only got one host galaxy in all of these?
No. What?
Can you get host galaxies for anything?
Oh, sorry. I thought you meant they've all come from the same galaxy. Right. Yeah, there's only one host galaxy in all of these. Yeah, absolutely. Now, most of them are binary black hole systems where you don't get an electromagnetic counterpart. The best of them, you get 20 or 30 square degree uncertainty on the sky location, and that's when Virgo is operating really well. So if you get 20 to 30 square degrees on the sky, that distance uncertainty is always a factor of 2 because you've got that inclination angle degeneracy with the distance. So that volume, that's not always true. You can slightly break that with higher order modes. But that volume that you get has a lot of galaxies in it. If anyone wants to quantify what a lot is, they're welcome to. But it's, you know, it's not tens, it's tens of thousands. So yeah, yep. But I mean, by the same token, other than for doing cosmology, do you care? Yeah, it might be interesting in terms of formation and things like that. But you're not going to pin down whether it's come from a globular cluster versus from the core versus the outskirts either. But yeah, it would be interesting. But we're a long way off being able to really pinpoint where these things are coming from. That's just hard.